Okay, let's take a look at this problem from 2011 USAJMO problem number 1. Find, with proof, all positive integers n for which 2 to the n plus 12 to the n plus 2011 to the n is a perfect square. And so first thing when I look at this, let's just try to choose some mod to take it. And so let's just choose mod 4, for example. And you know that a perfect square mod has to be congruent to 0 or 1 mod 4. So a perfect square must be congruent to 0 or 1 mod 4. So let's just take this mod 4. And so I'm going to say f of n is going to be this function, 2 to the n plus 12 to the n plus 2011 to the n. And so let's just try to take f of n mod 4. So f of n is going to be congruent to 2 to the n plus 2011 to the n. And you know what? 2011 to the n is actually 3 to the n. 3 to the n mod 4. So we only have to look at this much smaller and more manageable function when we look at mod 4. And so one thing to notice is that for all n which is greater than or equal to 2, we get that 2 to the n is going to be congruent to 0 mod 4. Since, if n is 2, then we have 4, or if it's 8, 16, 32, it's always going to be divisible by 4, so it's always going to have 0 mod 4. So this prompts something. This leaves out the special case of n equals 1. And first of all, I'd just like preclude here because we're not considering any n less than or equal to 0 does not work, because if, let's say, n equals 0, then we're just going to get f of n equals 3, and if n is less than 0, then f of n is not an integer. So we're only looking at n that's greater than 0, and so that leaves n is greater than 0, n is less than 2, that leaves n equals 1 is a special case where 2 to the 1 is not congruent to 0 mod 4. And so this prompts a casework. Specifically, the three cases are: first case is going to be n equals 1, second case is n is odd but not equal to 1, and then third case will be n is even. And we're prompted to look at parity here, specifically because 3 to the n, because this, you could also write this as 2 to the n plus minus 1 to the n mod 4. And so if this is odd, then this is going to be minus. If this is even, this is going to be plus. And so the parity makes it really easy to deal with this term. And so let's just go through these cases one by one. So I'm just going to start with case number 1, n equals 1. And so if we plug in n equals 1 to this equation, 2 to the n plus minus 1 to the n, we get 2 to the 1 plus minus 1 to the 1 is congruent to 2 minus 1 congruent to 1 mod 4. So there technically might be a possibility that this is a perfect square because congruent to 1 mod 4. So let's plug it in and test it out. 2 to the 1 plus 12 to the 1 plus 2011 to the 1 is going to equal 13, 2025, right? Yeah, because this is 14. Yeah, 2025, which is going to be equal to 45 squared. And so this is a perfect square, so n equals 1 is a perfect solution. So next, let's try the second case, where case number 2, n is odd but not equal to 1. So let's just take a look at this one. If n is odd, not equal to 1, that means we have n is equal to 3, 5, 7, 9, etc. And so each of these is always going to be greater than or equal to 2. So we get 2 to the n is going to be congruent to 0 mod 4. And if it's odd, then we get minus 1 to the n is going to be congruent to minus 1 mod 4. So you get in total that f of n is going to be congruent to 2 to the n plus minus 1 to the n, which is what we figured out earlier, which is going to be congruent to 0 minus 1, which is congruent to minus 1, or I guess minus 1 is 3. Whoops. Minus 1 is 3 mod 4. And so 3 is not 0 or 1, so there exists no, or I can just write there does not exist any solution, any n such that f of n is a perfect square. Not exist n such that n is a perfect square. There does not exist, I should probably say there does not exist odd n, which is not equal to 1, such that n is not a perfect square. So now let's try case 3. N is even. And since we're only considering n greater than 0, we get n is 2, 4, 6, 8, and so on. And so, well, this is always going to be greater than or equal to 2. So again, we have 2 to the n is going to be congruent to 0 mod 4 in this case. We also have that 3 to the n, or I guess minus 1 to the n, congruent to 1 mod 4. And so this doesn't really give us what we want, because we get that f of n is going to be congruent to 0 plus 1, which is going to be congruent to 1 mod 4. So this says that there does exist solutions, but if there does, then n has to be even. And so now we're not satisfied, so let's go one step further. Let's consider consider the residues taken mod 3. Because similarly to mod 4, a perfect square mod 3 must be congruent to 0 or 1 mod 3. Cannot be congruent to 2. So let's just try to use this equation, and I'll separate some space for it. So using this, a perfect square must be congruent to 0 or 1 mod 3. So let's just try to find f of n mod 3, which f of n is going to be congruent to, let's see, 2 is negative 1 to the n, plus 12 is congruent to 0 mod 3. So that's where like the 4 and the 3 come from, because that's the intuition there. And then 2011 is going to be congruent to 1 mod 3, since 2010 is divisible by 3. So it's negative 1 to the n plus 1 to the n mod 3, which is again a really nice expression and very, very simple. And now we only have to consider mod 3 for the case where n is even, because we know that if n is odd, there's only one solution, that n equals 1. So considering n is even, so n is even implies that minus 1 to the n congruent to 1, or is just equals 1. It doesn't really matter here. So minus 1 to the n equals 1. So we get f of n when n is even, which is going to be congruent to 1 plus 1, which is going to be congruent to 2 mod 3. And so that's not equal to 0 or 1, so there does not exist even n such that f of n is a, well, this should also say f of n is a perfect square, because we get a contradiction, or we get like a contradiction when we look at mod 3. So since the cases are exhaustive, the only possible answer is n equals 1. Because for any odd integers n that is not equal to 1, then we get a contradiction mod 4, where it's 3 mod 4, it has to be 0 or 1 mod 4. And if it's even, we look mod 3, and it's supposed to be 0 or 1 mod 3, but we get 2 mod 3, which is the one thing we can't have for a perfect square. And so therefore, n equals 1 is the only solution.